Szanowni Państwo, witam serdecznie na Wydziale Nauk Ścisłych i Technicznych Uniwersytetu Śląskiego. Myślę, że wszyscy doskonale wiemy, w jakim celu się dzisiaj widzimy, ale podkreślmy to, bo myślę, że to jest bardzo istotne. Po raz 17 odbędzie się uroczysty wykład pana profesora Andrzeja Lasoty. W imieniu pani dziekan, pani profesor Danuty Stróż, witam wszystkich Państwa bardzo serdecznie i bardzo się cieszę, reprezentując władze wydziałowe, że tego rodzaju wydarzenie u nas się odbywa, że jest już pewna tradycja tego wydarzenia, gdzie możemy nauki ścisłe popularyzować, promować i no jest mi z tego powodu niezmiernie miło. Chciałabym oczywiście życzyć Państwu udanego wykładu i dyskusji po niej. Wiem, że Pani dyrektor Katarzyna Horwacz zadbała o to, abyście Państwo mieli doskonałe warunki po wykładzie, żeby jeszcze porozmawiać, czy to z wykładowcą dzisiejszym, panem profesorem Rudnickim, czy po prostu ze swoimi kolegami i koleżankami. Także myślę, że ten dzień nie skończy się wykładem, ale bardzo konstruktywnymi rozmowami naukowymi. A teraz, nim uroczyście otworzymy dzisiejszy wykład, to myślę, że jest bardzo dobry moment, aby oddać też głos panu profesorowi Łukaszowi Stetnerowi, który co roku dba o to, aby jakość tej imprezy była na najwyższym poziomie. Także panie profesorze, bardzo serdecznie dziękuję za wszelki wkład, który pan profesor wkłada co roku.
Dziękuję bardzo. Proszę Państwa, ponieważ wykład ja przekazałem linki tego wykładu poprzednim laureatom, również cudzoziemcom, więc ja sobie pozwolę mówić po angielsku i tak samo wykład będzie po angielsku. So that, ladies and gentlemen, welcome to the 17th lecture, Professor Lasota lecture. Let me say that Lasota passed away on December 28, 2006, and starting from 2008, Faculty of Mathematics, Physics and Chemistry decided to organize every year a lecture to commemorate Professor Lasota. As you can see, there was so far 16 Professor Lasota lecture with one break because of pandemic time in 2021. We had no lecture, but the lecture was postponed to 2022, and then we had two lectures. And the last, our tradition is such that we have in 1 year we have a lecture presented by Polish speakers, and then we have by foreign speakers. The last foreign speaker was Professor Peter Inkele from Berlin, Humboldt University. And now let me say that there is a special chapter who is in charge of selection of Professor Lasota lecture. This chapter for a long time was served by Professor Roman Ger, and for the last couple of years I served this chapter. And as you have heard, today's lecture was chosen The lecture of today will be delivered by Professor Ryszard Rudnicki. Let me say a few words about Professor Rudnicki. Professor Rudnicki is a student of Professor Lasota. And Professor Rudnicki fields of interest of Professor Rudnicki is biomathematics, population dynamics, physiology, genetics, theory of Markov operators, partial differential equation, chaotic and ergodic properties of infinite-dimensional dynamical systems, probability methods in dynamical systems, and fractals. Professor Rudnicki was graduated from University of Silesia. His PhD was also at University of Silesia, as well as his habilitation. Since 2001, he is a full professor, and he's in the Institute of Mathematics, Polish Academy of Sciences. Professor Rudnicki has written 4 books and about 100 papers, and among his main contributions we have to mention solution of so-called Vogel alternative for Markov semigroup of Markov operators, as well as model of paralog families in the genome. So today Professor Rudnicki is going to talk about this will be rather personal lecture about with the title with Professor Lassota, There and Come Again. So first of all, I would like to give you a special diploma, and you can see.
Can I see?
Yeah. And now the floor is yours.
Okay. Dear Chairman, thank you for a very nice introduction. It's a great honor and pleasure for me to give a lecture dedicated to Andrzej Lassota. As the chairman said that I was his student, but not only. Well, you see, Andrzej Lassota, it is a special photo. He decided to take this photo, should be for every occasion. So it was very famous one. So, and I start with some very short presentation of his academic activities. Professor Lassota studied at Jagiellonian University. He started from physics, then mathematics. It is, in my opinion, the fact that he started from physics has a big influence on his research and thinking about the science. It was not typical mathematician, I must say. Okay, then he worked at Jagiellonian University for 20 years. He was a dean of the faculty, as you see. And then he started to work at the University of Silesia, also for 30 years, with a very short break in Lublin. And, but at this time, he has also a part-time position at the Jagiellonian University and at the Institute of Mathematics, Polish Academy of Sciences. It is very interesting because in 1976, I started to study mathematics at Silesia University, just exactly at the same year when he came to Katowice. And at the second year, I became his student. He has a lecture concerning differential equation, and I took part in this lecture. And after the exam, he proposed me to become his student, to make some thesis under his direction, so to be my master, something like that. Okay, but after study, I also worked at the Silesia University, but in 1994, I went to Institute of Mathematics, Polish Academy of Sciences, but I had a part job at the university, and Andrzej Lassota had a part job at academy, at our branch of the institute. So it was very funny time that he was my head at the university, and I was his head at the academy, at the Institute of Mathematics, Polish Academy of Sciences. So for about 10 years. Well, a few words about his activity. First of all, the main activity of him was differential equation, but when he came to our university, to Silesia University, he started to do a lot of things concerning dynamical systems, especially concerning chaotic behavior, ergodicity, some fractal theory, Moreover, he tried to study such properties of dynamical system by using Markov operators. So it's a application of some method from functional analysis to study properties of dynamical system. And the last thing, but not the least, were applications of mathematics in many branches, say in biology, physics, and also in technology. Well, so I will concentrate on two things. One are dynamical system, and the second are Markov operators. So my idea is to present some result of Andrzej Lassota, which has some influence on my scientific activity. There is one big problem because it's very difficult to choose exactly because this influence was rather great, but I should restrict to these two subjects. I mean the dynamical system and Markov operators, but I say something about application to biology. It's very, yeah. So, I started with some introduction. I hope sufficiently simple for students to understand what is going on in my lecture, okay? So first of all, we will study chaotic behavior of dynamical system. What is a dynamical system? In physics, it's simply method of describing of movement. So, if we have some, say, force which causes that the point moves, then the dynamical system describes this movement. But from the mathematical point of view, we have something like a metric space, a family of transformation which describe this movement. This family has some properties. As I said here, there is some semi-group property here, and as an example, we can consider an ordinary differential equation. So if we solve this ordinary differential equation with some boundary, with some initial condition, well, then the trajectory of solution of this differential equation is simply the trajectory of our semi-flow. So this semi-group of transformation is defined in this way here. Well, but we can also consider discrete time semi-flows. They are defined in a very simple way. We have one transformation of the space, and we consider iterates of the transformation, and this sequence of iterates define a discrete time semi-flow. So this is a subject of our talk, but, well, let me go to chaotic behavior. This masterpiece by Paweł Borysyenko show what an artist imagine what is a chaos. So look at this picture. We have some force outside of this picture which causes the movement of points. But this movement is rather very irregular. We can say that unpredictable, and moreover, it have some stochastic nature. So this is some expression of chaos, such a properties. But mathematicians need to have some definitions of chaos. So we try to formulate such a definition. Well, we can give some very general answer. A system is chaotic. It has, if it has a deterministic description, so this force is defined in a proper way, but it behaves in some, say, complicated, say, random way. This is a general description of chaotic behavior. But there are hundreds of different definitions of chaos, so we can consider three different approaches to such property. One is macroscopic approach, when we study attractors of a chaotic system, and if this attractor, so everything goes to some limit set called attractor, and if this attractor is a strange set, for example, if it's a fractal, then we say that the system is chaotic. The second approach is, say, microscopic approach, when we observe single trajectory of the system. So we are looking at the trajectories. If the trajectories behaves in some irregular way, then we can say that the system is chaotic. For example, if the trajectories are unstable, or if they fill the whole space, you can imagine the trajectory which fill a big space, for example, finite dimensional or infinite dimensional. It's a really chaotic property. There are also other definitions, turbulent trajectories, and so on. The last is topological mixing. I will give the definition after a moment. And the last approach to chaos is stochastic one. Instead of study single points, what is going on with single points, we study the distribution of points. So we start from some distribution of points and look what is going on with this distribution in time. And this description we can use some tools connected with ergodic theory. And I also give precise definition after a moment, but we want to have the measure to be invariant, so the transformation should preserve some measure and more mixing and so on. So I will not talking much about macroscopic approach, only concentrate to these two second and third definition. Let me say, we can consider microscopic approach. For example, we defined a chaos in the sense of Auslander-York if the system has two properties. Each trajectory is unstable, and the second, there exists a dense trajectory. Well, there is another definition of Devaney when we assume the property B and instead of A, we add that the set of periodic points is dense in the space. What is the topological mixing? Here is a formal definition. So you see, if we take two, say, open sets, non-empty open sets, and we fix one of these sets, say V, and we transfer by this dynamical system the set U, then after some time this set should intersect. It is also very nice definition of turbulent trajectory in the sense of Lassota-York. If the trajectory is compact, say relatively compact, and if it has no periodic points, then we say that this is a turbulent trajectory. You should imagine what can be that if you have a trajectory which has is relatively compact, so it's bounded in some sense, but it has not periodic points. It's not easy to imagine even such a trajectory. Now let's go to stochastic approach. So I said that the main notion is here is invariant measure. So the definition of invariant measure is given here on the top. It means that if we take any set, then the measure of this set does not change during the time. More advanced is the property of ergodicity. Look here at this formal definition with integral. Let f be a function from the space to R. Usually, such a function in physics is called observation. We observe the system. And on the left-hand side here, we have some limit. And this limit is simply the mean value of observation. On the right-hand side, we have also the mean value of observation, but with respect to this measure. So ergodicity means that if the observation is the mean value of observation in time, if the same as the mean value with respect to invariant measure. Especially if we take f as a characteristic function of some set, then this property denotes that the time of visiting of the given set A is eventually the same as the measure of this set. More advanced property is mixing. Look at this probabilistic definition, the second one. Here, P is the same as the measure mu. If we start from any set B, then conditional probability that the trajectory will visit the set A does not depend eventually on the set A, on the set B. So the beginning of the trajectory has no influence on the position of the trajectory in time, after a long time. And the last notion is exactness. It looks rather strange definition that if we start from even very small set but positive measure, then the measure of ST of A goes to 1. It means that very small perturbation has very high influence after a long time. Something like that. So sometimes people say that it's the same is with weather, that the movement of butterfly in Siberia can cause some changing of the weather in Florida, something like that, some hurricane or something like that. Well, the exactness is the strong property, and so they try to study such a mixing properties. And there is very nice connection between these two approaches, this microscopic and this stochastic one. For example, if we have a mixing measure which has extra property that this measure is supported on the whole space, so it means that it's positive on each open set, then immediately we have a chaos in the sense of Alexander-York. For example, ergodicity plus this property P, this positivity, gives that each trajectory is dense. Mixing plus this positivity gives instability, very strong instability of trajectories. And this ergodic mixing plus property P implies topological mixing. So there is a strict connection between these two approaches, and this ergodic approach gives better properties. You see on this picture is Andrzej Lasota and Jim York in Bendlevo. And below we have two papers of them. The first one is the paper which has most citation on Google, but more than 1,000. It is concentrated just the problems of invariant measure for piecewise monotonic transformation, for expanding transformation. And the second one also has a lot of citations. I don't remember, but what is interesting here, when there were introduced in this paper the notion of lower function. I would like to say something about them after a moment, but I would like to say what was the main tool to study, say, ergodic properties and, of course, in this sense, chaotic properties of dynamical system. The main tool was Frobenius-Perron operators. So we have some transformation of some space, measurable space, and we need to assume something. It's we assume that this transformation is non-singular. In reality, it means that we cannot transfer the set of positive measure to, for example, to a point to the set of measure 0. If we have such a property, then here we defined some operator on the space L1, and this operator is called Frobenius-Perron operator. But what exactly is this definition? Not formula. If we have some distribution of points in the space described by some density, so we have some distribution of points, and we take the action of dynamical system. So after the action of dynamical system, we obtain a new distribution, and this new distribution has exactly the density given by PSF. So the Frobenius-Perron operator say us what is the transformation of densities if we know the transformation of points. And there are very nice connection between properties of Frobenius-Perron operators and ergodic properties. Here, if we have some probability measure, which is absolutely continuous with respect to measure M, then we can take its density, and we can check that if the density is a fixed point of the operator, then the measure is invariant. If this fixed point is unique, then the measure is ergodic. If the iterates of the Frobenius-Perron operator of any other density converge to this invariant density, then the system is mixing. If we have strong convergence, then the system is exact. So we can transfer some notions which can be not easy to check from ergodic theory to the notion from functional analysis. And the method to study properties of dynamical system were by using some methods from functional analysis to study ergodic properties. Well, here is a book of Andrzej Lassota and Michael Mackey concerning just such a property. Half of this book is just exactly on this subject. And so you see on this photo Andrzej Lassota, Jim York, and Michael Mackey. It's also a photo from Bendlevo here. So we have Andrzej Lassota and Michael Mackey and Jim York were here the speakers of the Lassota lecture. Not only by Michael Mackey was Dr. honoris causa of the Silesia University. Well, some little generalization of Frobenius-Perron operators are Markov operators. Formally, the definition is very simple. Markov operators is a linear operator from L1 to L1, which preserves the set of densities. So if we take a density, then after the action of the Markov operator is also a density. Of course, Frobenius-Perron operator has such a property. And we can consider the system with continuous time when instead of Markov operator, we consider a family of Markov operators. So this family has extra semi-group property and some continuity. Such a notion has a lot of application, for example, to study stochastic processes, to study what is going on with a distribution of Markov properties. For example, we can study diffusion processes and piecewise deterministic Markov processes. I explain this notion. It's very nice one. And so, and for me, the most interesting property of, say, Markov operators is asymptotic stability. Like when we consider Frobenius-Perron operator, this asymptotic stability, the last notion here, was equivalent of exactness. So the asymptotic stability, it means that if we start from any density, then after a long time we approach this invariant density. So we will discuss about this thing. And I would like to present some result of Lassota and York on this subject, and then say something about possible generalization of this result. It is very interesting that, say, 50 years ago in mathematics, we can formulate the result in few lines, and it will be a real theorem. It's completely impossible now. So you can see the difference between mathematics, say, 50 years ago than now. So if we have a Markov operator or Markov semigroup such that if we start from any density f, then after a long time, pt of f will be greater than h. So h is some function which is the lower estimation of pf. It's bounced from the lower. So we call it lower function. If we have such a property, then this semi-group is asymptotically stable. So very simple notion, this lower function, and it gives immediately asymptotic stability. It has a lot of application, especially to dynamical systems, but not only. Look at the here is another definition, is the isomorphic definition, equivalent definition of the lower function. Look at this definition. Well, that we take a negative part of PTF minus H. If this negative part goes to 0 in L1, then we call it the lower function. Now, look here. This is from Jagiellonian University, this masterpiece, wall masterpiece at the Jagiellonian University. You see on this wall some number of formulas, okay? Maybe 3 or 4 here. Have you seen anything interesting here? Some fractals also, as you see on the corner. Yeah. Here there is the definition of the lower function. So it is, say, I hope that it preserves many years here. Well, I would like to say something about some generalization of this. If you want to generalize something, there should be some reason for it. So we are looking for some generalization which can be applied to some problems. And here is some result in this direction. instead of operators on L1, I consider the operators on the space of continuous function. We assume that X here is a compact half-dose space, and we consider continuous function. S plus, C plus of X is a positive function here. Alpha is some positive constants. And we replace the condition in Lassota-York theorem by the following one, that we have some estimation from below like that here, and if we have such estimation for sufficiently large n, and we need some compactness. It's impossible to do it without anything without compactness. And if for some, at least one function, if such a sequence is weakly compact, then what can we find? We can find some measure, mu, some positive constant, and some, say, function from some function f star is a positive function, such that maybe look only at the result here. If let's assume that f, for example, has is a density with respect to measure mu, then this thing is 1. Okay, so after some renormalization, the iterates of the density goes to the function f star. We have such a result. And it's a little different result than the lower function theorem, but it has a very similar application to something which looks strange at this moment. Application to some billiards with holes. So if you consider a movement of points in the space, but we make some holes in the space, and some points can go to the hole and they will be catched in the hole, and then we eliminate these points. So we only consider, say, here conditional probability, that we only consider here the distribution, not taking into account the points which goes to holes. What is going on with such a distribution? And moment, there was a paper of Pianigiani and York on this subject, sorry. I will say about some result and of them concerning this subject, not exactly the full formulation, but they consider, say, expanding maps such that our space is a subset of n-dimensional Euclidean space, but the transformation can go from X to a larger set. Okay? So, in this example, we have here such a situation that X is the interval 0, 1, but the transformation can, for some points, goes, the value of the transformation of some points can be greater than 1, so we eliminate these points and only consider conditional probability. Then, just for such expanding mappings, we can apply this theorem, this previous one, this for continuous function, to obtain the convergence. So it's the similar idea as in Lassota, where he applied this theorem for maps which goes from X to X. Here the maps can go also outside X. it's interesting that the set here, this measure, mu, is concentrated here on some Cantor sets. The idea of doing some theorems such that we assume that we have some estimation from below, some bound from below, can be considered later, was considered later, maybe about some generalization of this result. One of the generalization was in my paper with Lasota, where we consider a continuous version of this theorem, and very nice application. We have the following application. We have a movement of points on the circle with a constant speed, and from time to time we have jump. And the operator Q here describe as it's simply for example, a Frobenius-Perron operator corresponding to the jump function, jump transformation. So we have movement on the circle with jumps. And in having such a system, we prove some asymptotic properties of this system. This system is, in fact, piecewise deterministic. Because some movement is defined in a simple deterministic way, but we have from time to time some jumps. So at random times we have some jumps. I will give the definition of this piecewise deterministic system, but at that time we don't know that it is called piecewise deterministic system. So it's when we do this paper. And another generalization of this result was given by Lasota and York in 1996 to non-autonomous version, when we have not only one transformation, but we have a family transformation family of operators which can be different, something like that. So we explain the idea of some lower function, something like that, in a little different way. Instead of considering one function, we consider semigroups, Markov semigroups, which has such a property that if we take the action of this semigroup on a function, then this is greater than some integral operator. So we say it's a partially integral operator, or it is an operator with integral minorand, something like that. So we only assume about k that for some t, this k is non-trivial. It's non-negative and non-trivial. So if we have only such assumption, then if the semigroup has invariant density, and if this density is positive, then the semigroup is asymptotically stable. So it's very simple result in formulation that it's enough to have existence of density and their positivity. Then we have asymptotic stability. But the problem is that it is not easy to check the existence of invariant density. In some cases, yes, it's possible, in some not. So we are looking for some results which allow us to check properties of the semigroup of Markov operators without this assumption. And finally, we obtain some result about the decomposition of, say, partial integral semigroup. But here we need some extra condition. It's not the fact that the semi-group is partial integral is not enough. Here is some formulation here. So we consider a separable metric space, and we assume that this kernel, which bound the semi-group from below, is bounded from by such a function exactly that there exists for each point x0, there exists some neighborhood of this point, that this kernel is bounded by the same function in this neighborhood. For people who are interested in probability, it is easier probably to see here this formulation that the transition probability function is bounded from below by something like that. If we have such assumption, then we can prove a result concerning, say, decomposition of Markov semigroups. Here is the formulation of this result. There are some parts of this formulation, but what is interesting, we can divide the space X into some, say, set at this family of at least countable family of sets AJ and AI, and on each set we have a invariant density which is supported on this set, such that maybe we look at this part of the result. If our function is supported on the set A, then this alpha I is 1. So it means that we have asymptotic stability if the function goes from has the support from the set A. So on each set A, we have asymptotic stability. But outside of these sets, the sum of this set, we have some, say, sweeping property, which is given here, that if we look at the distribution on each compact set, then this distribution goes to 0. So I must say that if, for example, we don't have invariant density, so we have only this condition. This condition means, so if we don't have invariant density, then the space, then the Y is exactly all the space X, and the integral of PTF with respect to each compact set goes to 0. It means that everything is swept from each compact set. Such a nice property. So we use this thing as a kind of alternative. We have asymptotic stability or sweeping, something like that. And we can apply such result to many models. Mainly, we are interested in application to, say, piecewise deterministic Markov processes. What is a piecewise deterministic Markov process? Here is a formal definition. It's a stochastic process, Markov process, which has such a property that each trajectory, that we have a sequence of random times such that the sampler path, say, of this process, or trajectory of this process, is defined in a deterministic way in set A with time between Tn and Tn plus 1. So we divide the time on some periods when we have a deterministic definition, and at these points Tn we have some jumps. And what kind of jumps we can have here? We can have, for example, for example, a jump that the process is defined deterministically, and from time to time it jumps somewhere in the space. is one example. Another thing, it can be that we have many different dynamical system, and from time to time we change a dynamical system in a random way. So we have some dynamical system, change it, and so on and so on. And the last one is that we have some movement, and if we go to some obstacles, to some surface, for example, then we change the dynamics. For example, it can be a stochastic billiard, something like that. We write a book with Marta Tran-Kamińska on application of these piecewise deterministic processes. Hello. Just to biological models, so there are a lot of examples of such a system, but I only say a few words about it. For example, here is an example of a dynamical system with random jumps. So we have the dynamical system that the trajectories are going such a way, but if we start from some trajectory, go to some point, we jump somewhere else, then we go along another trajectory, jump to somewhere else, and so on and so on. So this is a random system, the dynamical system with random jumps. Such processes have many applications. For example, if we consider the growth of population with disaster, so the population is growing, 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 but suddenly, because some problems, the population goes down. So we have the deterministic process with jumps down. But more biological applications are given in these two papers are concerning immune system. How does it work, immune system? We have some antibodies which prevent us from some action of virus or bacteria or something like that. And normally, the number of antibodies goes to zero, simply decrease and so on. But if we have a contact with something, with bacteria and so on, then we produce some number of antibodies, so we have jump. So we have the process of decreasing and jumping. Is another example, and in these two papers we analyze such models, but it's more advanced thing. Here I do not go to details. Another thing are models of cell cycle. The cell cycle is the process which describes the position of a cell between beginning of its life and the end of the life. And during the life of a cell, we can have some changes. Especially at the end of the life cell, we have cell division and we obtain a new two cells. So usually the cell growing, and then cell, for example, at the division, it is divided into two new cells. Then we have some size or maturity less than before. So it's another process of this type. Another thing, I said something about processes with switching dynamics when we have some number of dynamical systems and we change the dynamics during the action of such a process. It's very good description of gene expression. What is the gene expression? It's a process of production of proteins and RNA particles, yes? And this production depends on the state of the system. Usually the system of production is given by some number of genes, and their activity or inactivity change the action of this system. So everything depends on activity and or inactivity of genes. We have, for example, one gene, the system acts in another way if gene is inactive, and another way when it's active. If gene is inactive, it does not produce RNA particles, for example. If it's active, it produces RNA particles, and these RNA particles are used to produce protein. So you see the description of gene expression is just the best way of, the simplest way by using processes with switching dynamics. Well, I wrote 2 books on this subject. They are unfortunately in Polish, but it's one is concerning deterministic systems, the second is concerning probabilistic. Well, and the last subject, till now, we are talking about dynamical system on the finite dimensional space. Okay, and you remember that the one very good tool to study the dynamical system in finite dimensional space were Frobenius-Perron operators. But what can we do in infinite dimensional space? For example, here is a very simple example of infinite dimensional system. We consider this partial differential equation. Solution of this equation depends on the initial function v, and we are here even able to know what is the solution of this equation. It's a very simple formula. You can ask, if you have such a simple formula, it can be chaotic. In some sense, it's very stupid. But in fact, it's a very chaotic system, that one. And I will like to say something about it. In fact, this system has some biological interpretation. This function u of tx describe here the distribution of cell maturity. So some model of cellular population, in fact. But I will go to some mathematical result. You see there are a lot of names here who work on very similar, on this system, on very similar one. Lassota started to do such a thing, so he was the first person who imagined that such a very simple system can be chaotic. So I present shortly his result on this subject. He proved that there exists a continuous ergodic measure. Continuous means that the set of periodic points has the measure 0, which is invariant with respect to this dynamical system. So, so we have ergodicity here. So it's some property of ergodicity is nice, but it's not so strong. His idea was to apply 2 results. One, some result with Jim York here concerning that transformation. If we have a continuous map such that if we find 2 sets, A and B, such that transformation of each set, A and set B, is greater than the sum of the set A and B, union of these sets. Then there exists a turbulent trajectory in the sense of Lassota-York. I mentioned before about such a thing, turbulent. And this thing and some old result of Krylov-Bogolubov that a continuous map of a compact set has invariant measure, has an invariant ergodic measure. So if we join these 2 facts, he proved the theorem 5. Well, but the problem was the following. Okay, we have some invariant measure, ergodic measure, but this measure can be concentrated on rather small set, for example. But if we want to prove some chaotic properties. We need something more. We need, for example, mixing property. We need positivity of the measure on any open set, something like that. The question is how to do it. And it was not easy to imagine how to solve such a problem. What can be the tool to do it? Well, and I started to work on such a subject, and I consider a little bit more advanced equation at that moment, but so it's a simple generalization here. So you can think about the previous equation, but I was able to prove that there exists a probability measure which is invariant with respect to this dynamical system, which is exact, so that's the strongest property, ergodic property, and it's positive on each open set, so it's supported on the whole space. And the question is how to prove it. First, I observed that our system is isomorphic with a very simple transformation, with a left shift transformation of translation transformation, given here. Oh, okay, we have isomorphism with translation. How to find an invariant measure? Okay, if we should look for some stochastic process, a stationary stochastic process. If you have a stationary stochastic process, then the distribution of trajectories in such a process are invariant with respect to the shift. So, translation transformation. So first we have some isomorphism, and then I need a proper, say, stationary process. It is Ornstein-Uhlenbeck process. It is defined here. If someone knows what is the Wiener process, then the definition of this process is very simple. One is given here. So instead of considering the semi-flow ST, it's enough to consider semi-flow TT. And then this measure given by, say, stationary Gaussian process is invariant with respect to this transformation. So if we define this measure, then we can go back to ST, and you obtain invariant measure with respect to ST. And so it was the proof of existence of invariant measure. Exactness was a little bit more advanced, but not too much. We use here some Blumenthal 0-1 law for Wiener process, and some another different definition, equivalent definition of exactness. And the last one, positivity, is also very simple, because the Wiener process has such a property that if we take two functions, one f is smaller than g, on some interval AB, then the set of all trajectories which are between f and g has a positive measure. So in this way, I prove positivity. Okay. So it was another way of approach to study this infinite dimensional dynamical system. The problem, this method can be applied to many other interesting dynamical systems. One is connected with the dynamics of maturity of blood cells in the bone marrow. Do you know where blood cells are produced? All blood cells are produced in bone marrow. What is a bone marrow? In Polish, szpik kostny. Okay, but in this bone marrow, we have two processes. One is division of cells, And the second is maturity. So the cells during the life, we start from very simple cells, and these cells change. After each division, they change to make more complicated, more advanced, more, maybe not complicated, more advanced. And just at the end, just at the moment when they go out of the bone marrow, they lost, both red cells, for example, lost no kernel, jądro. No kernel. Okay. They go to the blood system, okay? So they can divide in the bone marrow and make more and more mature. So you see on this picture, we started from this white one, and then in time they became more matured, but they can divide here, so we can have division. I said nucleus, rather. But this process is regulated by some hormone, erythropoietin, and this hormone regulates how the system works. But if we don't have this regulation, we can consider a very simple process that the number of cells in the bone marrow, say, assume that is a constant. And if one cell is going out from the bone marrow, we simply assume that one cell inside, we have a division of one cell, to have a constant number of cells in the bone marrow. Very simple process. One is leaving the bone marrow, one is divided. We choose this cell here to division in some random way, only depending on the distribution of the cells here. So this process is described by such nonlinear equation, but we can say, we can prove asymptotic, we can prove chaotic behavior on all meaning we consider here. Another application was to this equation with a typical size model in population dynamics. You see here there is some extra term, non-local term here, and also in this case I was able to prove some chaotic properties, some existence of invariant measure, but the proof was much more advanced here. And recently I received two results. The first one, as you see, it was published in this year, in the last year, when we consider n-dimensional system. The problem was how to replace a stochastic process and this shift transformation. And I use here, instead of, say, stochastic process, I use Levy d-parameter Brownian motion is a stochastic field. Stochastic field is a process but not defined on a line. The time is not real numbers, but from R1 or RD in d-dimensional space here. And completely last result is a Heat equation. Nobody thinks that Heat equation can be chaotic in any sense. We consider a Heat equation here, and this is on the positive half of the line, this Heat equation. And we have some boundary condition, Neumann boundary condition, that normally, if we have this heat equation, then solution of it goes to 0. If we start from, for example, the integrable function. But if we change the space in some sense, the initial function, consider an initial function which can grow sufficiently quickly, like here, then we obtain the existence of invariant measure having such a properties I said before, so mixing and so on and so on. It's not published yet, but new result. We just near at the end of our talk, so I said only about a few results which were in some sense connected with Andrzej Lassota, but what was also another things which are interesting, which we study. One are models of the cell cycle, such problems were very useful to develop the theory of Markov operators, some new results concerning asymptotic stability, sweeping, and so on. Another things are structured population models. We usually, when we consider the population of some individuals, then we assume that these individuals are described in some sense. For example, they can have age, size, and so on. So structured population are some partial differential equation which describe the distribution of such a properties as size, for example, or age. Nonlinear population with delay, probably we have had, there is a very well-known paper of Lassota concerning some model of blood production system. So we consider with Michael Mackey some generalization of his models where we have some delay or something like that. And the last but not the least is the thing which started from the Boltzmann equation. We have Boltzmann equation describes the movement of particles in the space with some jump, with some heatings and so on. They were interested in the distribution of velocity. This distribution is described by by some linear equation, but with nonlinear term here, by some equation with nonlinear term. So this equation were studied by a lot of people, but at some time I started to work with my PhD student Paweł Zwoleński on some phenotypic model. So in some sense completely different thing. But if we consider a distribution of a population according to some phenotype, we can consider phenotype for size of an individual can be a phenotype or something like that, some properties of the individual. These models were in some sense very similar to a model of Boltzmann gas, because we have very similar things here. In Boltzmann, particles can hit each other. Here we have some individual should meet to produce a new individual. And finally, we prove some results, some asymptotic result, which generalize earlier result on this subject, connected with the Boltzmann equation. So, so the end of my talk is what we should take to home, something like that. First of all, from the very beginning of my talk, I told about Markov operators, about Frobenius-Perron operators that are very useful tools to study chaotic and ergodic properties of dynamical system. The second thing is that we can use Markov semigroup to study some diffusion processes, what is going on with the distribution of diffusion processes, piecewise deterministic processes, and some hybrid system, and so on. The last thing was chaotic properties of infinite dimensional systems given by partial differential equation. And as you see, the using of stochastic processes can be very useful to study such system. And the last thing is application to biology. Biology provides us a lot of models which are very interesting because they are some different than physical models. We can study this, when we study such models, we can develop some mathematics, some new tools in mathematics, so we can prove some new results. And finally, in conclusion, it's something for future. It's some quote from Sir Roy Collins, from the head of clinical research at Oxford University. If you want a career in medicine these days, you're better off studying mathematics or computing than biology. So you see what is the tendency in science. Thank you very much for your attention.
Okay, so now we have a possibility for remarks, comments, and questions to our speaker. So at the moment I don't see, so I start with my questions, and in the meantime, hope there will be more questions. Okay, but now question will be in English. My question is as follows. At the first of your talk, it was important for you, at certain moment you assumed that there exists invariant density,
Yes.
and you also wanted to have unique invariant density. So, for me it seems to be rather assumptions to get such property.
Well, usually we have a dynamical system. We can divide the space into parts. You have a unique invariant density. As in this theorem I presented about the decomposition of a Markov semigroup. Then we usually first divide the space into different parts when we have ergodicity.
Yeah, but
Your decomposition, you could have many such,
Yeah.
let's say,
No, we can have
table.
a countable number of. But the problem is with communication between states. If we are able to prove that we are able to communicate between different points in the space, then we have unique invariant density.
Yeah, so this is quite, because
Yeah. Yeah.
Another question is this one. If you are talking about piecewise deterministic,
Yeah.
so you assume that the time between jumps
was
No. I do not assume such a thing. Okay. In the paper, very good question. I like this question, but as you remember, I quoted some paper, maybe concerning immunological system. In this paper, we consider the system when we don't have a Markov property. We have such a thing that we have a process, but jumps between them is described by any random variable. So we have no Markov property in any way, but we can replace such a system by a Markovian one, introducing extra coordinates, extra variable. Yeah, if we take if the dimension was greater, then if we should find a proper Markov process. Usually we should extend the space to have Markov property.
Other questions or comments? Another comment for an audience. So, biology. Very general, because I would like to know whether Markov processes are natural to describe in biology, or this is just an approach which we can use, because once we have Markov processes, we have certain tools and we can calculate something. But is it natural in your biological problems, or approximate?
Okay. You can build a model, Markov model or not Markov model for the same phenomenon. You can build a lot of models. But the problem is different. The problem is what we can observe, what we can measure. Sometimes we can measure such things which are not possible to include in the Markovian description. For example, if we consider a population, a cellular population, then we can measure the time between the division of cells. And we formally cannot assume that it's exponential distribution, something like that. Because if we measure it, the result will be completely different. So we should check if our assumption is proper. It's connected with experimental results. So it's better to build more general problems than you omit the problem of checking Markov properties. So if you consider non-Markovian model. So this is a question of experiments, not a question of models.
I don't see. So let's thank our speaker once again. And let me say a few words about our program. So right now we have, let's say, 30 minutes break for catering outside, and afterwards we are planning to have concert. So